Welcome to the video lecture on Fourier series. This is the continued part of the previous session, that is this the session number 2. We shall see the Fourier series expansion of the function in the interval 0 to 2. Before going to the concept, we shall see what are the things that is required for expanding the given function in as a Fourier series in the interval 0 to 2L. So first of all, you should know what are the Dirichlet's conditions. A function has to satisfy Dirichlet's condition to expand it in Fourier series, and also you should know the properties of definite integrals and the techniques of integration. The Fourier series expansion of the given function in the interval 0 to 2L, where f of x is a periodic function defined over the interval 0 to 2L, is given by this formula. You should remember this one, as I already explained this one. F of x is equal to a0 by 2 plus and so on, where a0, a and bn are the Fourier constants or Euler constant given by these formulas. Now a0 is equal to 1 by L times integral 0 to 2L f of x dx and so on, and an and bn formulas are there. Now with this, let us see some problems on this. Find the Fourier series of f of x is equal to x over 0 comma 10. Here you first calculate the length of the interval. 2L is equal to 10, therefore the value of L is equal to 5. So the first Fourier constant is given by a0 is equal to 1 by 5 times 0 to 10 f of x dx, and after integration, after substituting f of x is equal to x and integrating, you will get 1 by 5 times x square by 2 between 0 to 10, and the final value turns out to be 10. So the value of a0 is equal to 10. Problem. And an is given by 1 by 5 times integral 0 to 10 f of x cos n pi x by L, where L is equal to 5 into dx. Substituting the value of x, integrating by parts, we are going to get this, and after applying the limits of integration, so you are going to get 0, because we get here 5 by n square pi square minus 5 square by n square pi square, so both gets cancelled. We get the value of an to be equal to 0 for this problem. Now to find the value of bn, you write down the formula 1 by 5 times integral 0 to 10 f of x sin n pi x by 5 into dx. So substitute f of x here, f of x is equal to x, and then integrate by parts. 1 by 5 times, first into integral of sin is minus cos n pi x by 5 by n pi by 5 minus derivative of x is 1 minus integral of this term is minus sin n pi x by 5 into n pi by 5 whole square between the limits 0 to 10. Apply the limits of integration, we get 1 by 5 times, this is the upper integral part. Upper integral part is, I have put x is equal to 5 here, so we get cos 2 n pi, where cos 2, that is 10 if I substitute, 5 ones are 5 twos are, so cos 2 n pi we get. So cos 2 n pi is, so plus 1, so we get minus 10 into 5 by n pi minus, and this is the lower integral term, so here we get x 0, and here sin 0 is 0, so we get lower term is 0, so 5 gets cancelled. Finally the answer is minus 10 by n pi. Therefore the Fourier series expansion of f of x is given by, substitute all the Fourier constants a0, an and bn, so you are going to get this expansion. Here n is equal to 0. Go on expanding by putting n is equal to 1, 2, 3, etc. So we get this series. This is the Fourier series expansion of the given function. Now let's have a look at the second problem. F of x is equal to 2x minus x square, which is defined over the interval 0 to 2, and also deduce this series pi square by 12 is equal to sigma n is equal to 1 to infinity minus 1 power n plus 1 by n square. You calculate the length of the interval. Length of the interval L is equal to 1, and the first Fourier constant a0, and it is given by 4 by 3. The second Fourier constant an, substitute f of x after writing down the formula and integrate this. So after integrating and substituting, so integrate here by using Leibniz rule, so we get 2x minus x square into integral of cos is sin n pi x by n pi minus derivative of this is 2 minus 2x. I have already explained this one, and integral of this is minus cos n pi x by n square. Derivative of this term is minus 2, integral of this term is this. So after applying the limits of integration, you will get minus 4 by n square pi square. So and third Fourier constant Bn, substitute f of x here after writing the formula and integrate by parts or Leibniz rule, we are going to get, so the Bn is 0. Therefore the Fourier series expansion of f of x is given by this formula. Substitute all the constants, you will get this one. So now if I put x is equal to 1 in this expression, you will get the required series. These are all the sum of the exercise problems. You can work it out. Thank you.